All right, so we've talked about Lewis structures in general and how we're going to be sharing electrons in order to fill the valence shell of all of those different atoms. But what we're going to see here in these next couple of slides is there's going to be a few exceptions where we're not always going to have that be the case. And they kind of fall into one of three different categories. The first one's just going to be when we have an odd number of electrons to work with. So remember, the first thing we always need to do if we're trying to go from a chemical formula to a Lewis structure, no matter what the substance is, we need to figure out how many valence electrons do we have to work with. So we've got to look at that chemical formula, see what elements we have, how many of each of those do we have, and then use the periodic table to calculate the total number. So if we wind up with something like NO, one nitrogen with one oxygen, nitrogen group 15 is going to give us 5 valence electrons. Oxygen group 16 is going to give us 6, so we're going to have 11 total to work with. But because we've got an odd number there, we're just not possibly going to be able to fill the valence shell, because remember, that's going to require 8 electrons for most atoms, with the exception of hydrogen in period 1. But because they need that full valence shell, they need that even number. If we've got an odd number to work with, we're automatically just going to be thrown off a little bit. So when we look at the Lewis structure for NO, we can see we've got 2 different options, and it's pretty close to having a full valence shell. We can almost get there, but in each case, we're going to wind up with one atom that's just missing 1 electron. And again, it's because we have an odd number to work with. But if we look at it, you can think about it in either case, we're kind of just switching the atoms around here. So in each case, we've got a double bond representing 4 electrons that count for the nitrogen and the oxygen. But then in the first structure here on the left, we've got 3 more electrons around nitrogen, 4 more around oxygen. So in this case, nitrogen's only got 7, but oxygen has all 8 it needs. And then if we count the total number, we've got 4 more here to give us 8 total. 9, 10, and 11. So we've used the correct number, which is we can't possibly fill the valence shell of both of these just because we have an odd number. But we could have also come up with a structure like we see on the right here. And in this case, we're essentially just switching the electrons at the bottom. So now nitrogen has a full valence shell. Oxygen is just missing 1. And in the case where we've got an unpaired electron, like we have at the bottom of nitrogen on the left or the bottom of oxygen on the right, that's what's known as a radical. And those are going to be extremely unstable. They're going to be extremely reactive. And if you think about it, all of these atoms want to get to a full valence shell. So now these atoms are just 1 electron away. So they're going to have a higher affinity for electrons now. So they're just going to be looking for something that they can essentially take an electron from in order to get that full valence shell. So because they're missing that 1 electron, they really want to gain 1 more. That's why they're going to be so reactive. That's why they're going to be so unstable. But if we think about both of these structures and we want to think about which one's going to be more correct, again, we can always use the formal charge. And if we calculate the formal charge of and I'll use the pen now. Whoops, no. If we calculate the formal charge for the nitrogen in the left structure, again, nitrogen is going to have 5 valence electrons. In this case, it's got 3 on its own. And then it's got 2 in the lone pairs. So we've got a 0 for nitrogen there. And then if we do the same thing for the oxygen, 6 minus, it's got 4 on its own. And again, the 6 is just how many valence electrons an oxygen atom is going to have. And then it's got 4 on its own, and then 1/2 of the bonded electrons, or just the number of bonds. So we've got 2 here because it's a double bond. So in each case, with the left structure, we wind up with nitrogen and oxygen both having oxidation numbers of 0. So that's going to be our structure. We can't minimize it any further. But if we look at the other structure, we can see why this would be even more unlikely, or why it's going to be even more unstable if we actually had this structure. Because now with the nitrogen, still 5 valence electrons, but now it's got 4 on its own, and then it's got 2 in that double bond. So now nitrogen is going to have a -1 formal charge, which we don't even have to calculate the oxygen. It's going to have to be +1 in order to balance it, because this is neutral overall. Same reason why both of these the nitrogen and the oxygen 0 and 0 both add up to 0 because it's a neutral molecule. But now if we also think about those formal charges, -1 and +1 obviously are larger than 0 and 0. But if we also think about those elements, oxygen is going to be more electronegative than nitrogen. Oxygen is going to have a stronger affinity for those electrons. So it would make more sense for oxygen to be able to take the electrons and fill its valence shell like we see on the left, whereas the nitrogen, less electronegative, should be the one that's electron deficient, the one that doesn't have a full valence shell. And then in other cases, we're just going to have certain elements that just are going to be sort of okay without a full valence shell. And we'll see that with the boron here. So if we think about the structure for BF3, boron trifluoride, if we wanted to get the structure, we could calculate the number of valence electrons. We'll get 3 from boron because it's group 13. We'll get 21 from the 3 fluorines combined, so we'll get 24 overall. And then if we want to fill the valence shell of all of these different atoms, what that's going to require is a double bond between the boron and one of those fluorines. But when we do that, you'll notice what we got possible resonance structures because we could have that double bond going to any of the fluorines. But when we do that and take a look at the formal charges, fluorine, for the fluorines that are single bonded to boron, those are going to have an oxidation number of 0. And for this, you can just focus on one of those structures. So if you want to look at just the left one, they're all equivalent, so it doesn't matter which one we focus on. But both of these fluorines on the bottom of that left-hand structure, both have a formal charge of 0, whereas the top one, the double bonded one, now is going to be +1, which means the boron in the center, to balance that out because it's going to be a neutral molecule, has to be -1. And in terms of the formal charges, those aren't very high. So those are fairly minimized, just about as good as they can get, other than just zeros across the board. So the formal charges themselves, in terms of the magnitude of them, isn't really an issue with this one. And we've, like I said, filled the valence shell of all of these atoms. We've used the correct number. So we've kind of checked a lot of the boxes that we've talked about. But again, if we think about the sign of the formal charges, just like we did for the NO radical on the previous one, it wouldn't really make sense for the fluorine to be +1 and the boron to be -1. Fluorine is going to be the most electronegative element. So if anything's going to be negative in a compound with fluorine, it's going to be the fluorine. So with that structure, it really doesn't make a ton of sense just based on those formal charges. So what we're going to see in this case is boron is actually okay being electron deficient. So boron's actually okay just having the 6 electrons like we see on the right hand or the left hand side here. And now by doing this, if we look at the formal charges, again, we saw in the previous slide, single bonded fluorines that have then a full valence shell from the lone pairs have a formal charge of 0. So now all 3 of these fluorines have a formal charge of 0. The boron also going to have a formal charge of 0. It's going to have 3 valence electrons as a free atom. It's got no valence electrons on its own, and then it's got 3 bonds to it. So 3 - 0 - 3. We have a formal charge of 0 now for all of those different atoms. So when we're looking at fewer than 8 electrons, and of course with this one we're excluding the period 1 elements, so hydrogen and helium, just because those are okay with the duet. But when we're looking about the rest of the elements that want to have typically want to have a full valence shell, we're going to be okay sort of neglecting that if it's a situation like this where the central atom would actually wind up with a negative charge if we filled its valence shell. So with the boron, where we get that double bond involved, because that then makes the boron negative and the fluorine positive, that's why we're just going to see the boron be electron deficient. It's just a better setup. It's more stable overall, just to keep it with the 3 bonds rather than the double bond to fill the octet. And again, we're just thinking about the electronegativity there. So since fluorine is the most electronegative, fluorine's more electronegative than boron. If either of those elements is going to be negative, it should be the fluorine. And I should say, with all of these, we're going to look at the exceptions, and then we'll get a ton of practice with a bunch of different examples. And then we'll actually see, we can do just the opposites of boron, just had less than 8 electrons. In certain cases, we're going to be able to exceed the octet. So we can be electron deficient. In some cases, we can also exceed the octet in the others. And in this case, what we're going to be looking at is, or the only elements that can do this are going to be elements in the third period and below. Because in that case, once we get to the third period, so once we're thinking about things like phosphorus or sulfur, once we get to that point, we think about the electron configuration. We're in the third energy level. We've got 3s, 3p. But also in that third energy level, there's the 3d block. So now that we have that, those d orbitals available, that's why we can kind of just pack on extra electrons to certain elements and actually exceed that octet. So if we think about something like phosphorus pentachloride, PCl5, 1 phosphorus with 5 chlorines, just by bonding all of those chlorines to phosphorus, we're automatically going to exceed that octet. But like I said, because phosphorus is in that third period, it now has that 3d orbital, or the 3d subshell available. So the 9th and the 10th electron, we can kind of just add into that subshell. But again, with it, only the third period and below. So when we're looking at things like carbon, nitrogen, oxygen, fluorine, the second period elements, they are not going to be able to exceed the octet. So we can never wind up with more than 8 electrons around those. So if we look at an example here for the phosphate ion, so PO4, so 1 phosphorus, 4 oxygens, and then it's got a -3 charge overall. So with this one, just note that I think I mentioned this in one of the earlier sections of this chapter, but just note with the Lewis structures for polyatomic ions, in terms of getting the structure itself, it's still going to be the same. We've got that extra piece in terms of considering the charge, how that affects the number of valence electrons. So in this case, we would do 1 phosphorus gives us 5 valence electrons. Each of the oxygen gives us 6. So we get 24 from there, 5 from the phosphorus for 29. But then we've got this -3 charge. So we'd really have 32 electrons overall. We've got to account for that charge now. So with the ions, we've got to account for the charge. But then getting the structure is going to be the same as it would for a molecule. It's just once we get that structure, then we're going to put it in brackets and then just put whatever that charge is to the top right. So just like when we're looking at the formula, PO4 3-, we can quickly look at it and see 1 phosphorus, 4 oxygens, and then a -3 charge overall. We want to include this in the structure just so that when somebody's looking at that Lewis structure now, they can quickly tell that it's going to have a -3 charge overall. But when we look at the Lewis structure for phosphate, if we just did a single bond between the central phosphorus and all 4 of those oxygens, and then just filled in the valence shell of each of them, what we're going to see in that case is it uses the correct number of electrons overall, so it uses 32, and it fills the valence shell of each of them. But when we look at the formal charges, all of these oxygens are going to be -1, and then the central phosphorus is just going to be +1, so it still balances out to -3. But because phosphorus is in the third period, phosphorus can now exceed that octet. So what we can do actually is take the lone pair from one of these oxygens and just move it into a double bond. So when we do that, we still keep 8 electrons around the oxygen here. It's just now we're sharing them differently. Now we're sharing them in a double bond and 2 lone pairs rather than a single bond and 3 lone pairs. But by doing that, we change the formal charge of that oxygen down to 0. And then we do the same thing with the phosphorus. It now becomes 0 as well. So now the only things with a charge are 3 of the oxygen, still balances out to -3. But because we've minimized the formal charges, we've reduced the number of atoms that actually have a formal charge that's not 0. This would just be the preferred structure. And then with this one, again, we would really have resonance because we could put the double bond on the left. We could have put it on the bottom, the right, the top, wherever, and it would still be the same thing. So we'd have that resonance structure for a phosphate ion. And you can just see the kind of the bullet point or the main takeaway there. The lesson is when the central atom is in the third period or below, or third row or below. Remember, row and period are synonymous. Expanding its octet is what we want to do if it's going to eliminate some of those formal charges. So in this case, by expanding the octet on that phosphorus, we change the formal charges of two of those atoms from plus or minus 1 to just 0. So that's just going to be a more favorable structure. And in some cases, we may have to double bond a second oxygen. So instead of 10 electrons around the central atom, we might wind up with like 12 or something like that. So it's going to be something that you'll have to practice with. And like I said, we'll see a few examples. And then there's extra on Canvas too, but it's just going to be whenever you get a structure, always just double check the formal charges just to see if it's a possible structure or not. And when I say possible structure, if you have really large formal charges, that's going to be an indicator that it's probably pretty far off. You might have the central atom incorrect or something like that. But if you wind up with something like the one on the left here where everything has a formal charge, just see if there's anything you can do, any way you can switch those electrons around. And the easiest and typically the only way that we're really going to see that is just by expanding the octet on that central atom. So always just double check to see what element you have there, where is it on the periodic table, to see if expanding that octet is even an option. Because like I said, it's only going to be in that third period and below. So if we had nitrogen, for instance, so right above phosphorus, we wouldn't be able to expand the octet just because it's in the second period. It doesn't have that D subshell available in that energy level. And with it, what I think I'll actually do is just, because I think the rest of these are all just a bunch of practice. Actually, we'll look at two of them just because I've got the bond strength. All right, so if you want to practice with these ones, just kind of give yourself a chance by pausing the video. I'm just going to start to work through them though. But like I said earlier, the first thing we always want to do is figure out how many valence electrons do we have to work with. So what we can do is kind of just make a little table, list the different elements, and in this case, we don't really have too much to do because we've just got one of each of them. So one nitrogen will give us 5, one oxygen will give us 6. So we'll wind up with 11 total. But then in this case, we're looking at an ion. So we've got to account for that positive charge now. And with it, it's a little bit backwards. Remember, electrons themselves are negative. So if we have a positive charge, that means we lost a negative. So what we're really going to do is just subtract 1, and we'll wind up with 10. So in this case, we're going to have 10 electrons to distribute around the nitrogen and the oxygen in order to fill the valence shell of both of these atoms. And in this case, since we've got an even number, unlike the radical that we saw, just NO without the charge, in this case, since we've got an even number, we will be able to fill the valence shell of both of those atoms. And for this one, we don't really need to worry about what is the central atom at all, just because we've only got 2 atoms. So we'll just do nitrogen, oxygen, and then we can do a single bond. And with this, from this point, think about it, we've got 10 electrons to use. That single bond now uses 2. So what we can do is I'll start with the oxygen, because that's more electronegative, so we'll fill that one in. It'll be better at gaining the electrons. So we'll fill that in. And then the best I can do for the nitrogen is just that one set of lone pairs. So you can see I added 6 dots around the oxygen. I added 3 sets of lone pairs there to fill the valence shell of this oxygen. And then I'm using my tablet and then recording it on my laptop for the audio. So hopefully you can still see the mouse on the recording. I didn't think about that or not. But on the oxygen there, now we have a full valence shell. But because that uses 8 electrons, we've only got 2 left over for the nitrogen. So now with the nitrogen, we're missing 4 overall. So what we're going to have to do now is go back and remove some of these lone pairs. Nitrogen needs 4 more. So that means we need to take 4 of oxygens and move them into that bond. So we're going to wind up with a triple bond, and then each of them having just 1 lone pair on their own. But remember, with the ions, we've got to account for the charge when we're calculating the valence electron. So that's why we subtracted 1 to get 10 overall. But then at the end, we're just going to put the entire structure in brackets, and then whatever that charge is, in this case, just the +1, we'll put to the top right of it. So now this is clearly showing we've got a nitrogen and an oxygen triple bonded together, and then there's a positive charge overall on that structure. And if we looked at the formal charges of these ones, what we would see is that the nitrogen is 0, and then the oxygen is +1. So this would be, I'm not too familiar with this ion, but based on those formal charges, I would assume this is going to be a relatively reactive ion, just because it has the positive oxygen. And then with this also, so let me clear this before we start looking at the next one. Oops. Okay. With this, hopefully you're starting to also see with these formal charges, for instance, oxygen here, we can see with a double bond at 0. And then if we think about oxygen, it's got 6 electrons on its own, so it needs to gain 2 more. So that's why oxygen typically wants 2 bonds. Could be in a double bond, or it could be in 2 different single bonds. But the preferred state for oxygen is always going to be 2 bonds. And then if we go back and look at chlorine here, or anytime we have fluorine, typically we're going to see that those have single bonds, at least in the case where it's got a formal charge of 0. And that's going to be because the halogens have 7 electrons to begin with. So they only need 1 more electron. They only want to form 1 more bond to gain that extra electron. Nitrogen, if we go to the, I erased it, but if we think about the structure we just drew for the NO plus ion, had a formal charge of 0 because it had a triple bond and then just 1 set of lone pairs. So nitrogen on its own, 5 valence electrons, it's missing 3 of them. So nitrogen typically wants to have 3 bonds. So you can kind of use the group of the periodic table, how far away it is from the noble gases, to think about how many bonds does it want to form to fill its valence shell. And if it forms that many, typically, as long as there's nothing weird going on with either lone paired, we'll see it's got a formal charge of 0 in that case. But then if it's got more or less bonds, that's where we'll start to see the positive and the negative formal charges. Okay, but then for the second one, we can start exactly the same. Carbon and hydrogen. In this case, we've got 2 carbons. Each of them in group 14 will give us 4 valence electrons. We've got 4 hydrogens that are each just going to give us 1. So we've got 8 and 4. So we've got 12 valence electrons total to work with. And again, for this one, since it's neutral overall, we don't need to account for any charge. But with this one, this is going to be an example of an organic molecule. So remember, organic chemistry is the study of carbon. We looked at, when I was talking about resonance earlier in the chapter, we looked at the resonance structure for benzene, just that carbon ring, 6 carbons with hydrogens, with 1 hydrogen attached to each of them. So with these organic molecules, and actually just with anything that contains hydrogen in general, just remember hydrogen has to be on the outside because hydrogen can only form 1 bond. So we can't put hydrogen in the middle because then it would be able to bond to something on one side, but it would have nothing else to bond with on the other. It wouldn't be able to form a second bond. So these 4 hydrogens have to be on the outside. And then also with carbon, pretty much all of the time, it's going to form 4 bonds. So when we're thinking about these organic molecules, if we've got a hydrocarbon, so you think about hydrocarbon telling us hydrogen and carbon bonded together, what we're going to see is essentially the carbons are just going to be attached to each other. And then just branching off of those, we'll just have the hydrogens. In some cases, if there's a lot more carbons, there's kind of different ways we could draw them, but we don't need to worry about that for this course. But like I said, we're going to have the carbons bonded to each other and then the hydrogens branching off. So what we can do is just take 2 of those hydrogens and attach them to each. And now when we look at what we've got here, how many of electrons we've used, remember each of these dashed lines represents a single bond that contains 2 valence electrons. So we've got 5 single bonds total. It means we've used 10 electrons overall. And if we think about the valence shell of these different atoms, all of these hydrogens are okay. They're all happy. They've got the one bond they need. So they've got the 2 valence electrons to fill that first electron shell. But then when we look at the carbons, now each of those is involved in 3 bonds. So each of these have 6 electrons total. So what we need to do is, with those final 2 electrons, just form a double bond here. Because now we've used 12 electrons total. We've got 2 electrons for each of the hydrogens. And now these 2 carbons in the middle each have a full valence shell, each have 8 valence electrons around them. So with the hydrocarbons and these organic molecules, what we're going to see, like I said, is that the carbons are typically going to be attached. And then we may see a few more examples, especially with the lab. But we'll kind of see how we can take that formula and kind of use it as a guide, because in some cases they're a little bit more tricky, but in other cases, the way the formula is written may kind of tell us how those atoms are bonded to each other. But for the most part, we'll be focused on things more like A, even if they're not always a charge or an ion. Okay. But again, if you want to practice with this one, just take a moment on to pause it and work on your own. But we've got to figure out how many valence electrons we've got. And we've got 1 bromine that'll give us 7. We've got 3 oxygens that are going to give us 6 each. So that'll give us 18, giving us 25 total. But again, we've got an ion. I believe this is the bromate ion. So we've got to account for that charge. In this case, it's -1. So we've got 1 additional negative piece. We've got 1 additional electron. So we'll do 25 plus 1, giving us 26 overall. So we've got to figure out how can we take 26 electrons and distribute them around 1 bromine and 3 oxygens to fill the valence shell. And with this one, again, the less electronegative one typically going to be in the middle. The one, if there's only a single atom of one of the elements and multiple of the other, the thing by itself will typically be in the middle. So we know that the bromine is going to be our central piece. And then I'll just put the oxygens on the outside, do a single bond. And then we'll fill in the valence shell of each of these oxygens. So we'll do 6 electrons around each of them. And then when we do this, we've used 6 in the 3 bonds, and then we have 6 on each of the oxygens individually. So at this point, we've used 24. Again, hopefully the mouse is showing up, but again, 6, 12, 18, just on the lone pairs around those oxygens. And then we've got 20, 22, 24, just in the 3 bonds. But we had 26 to work with, so we've got 2 more electrons here. So we can just add them to the bromine. And what that does is fill the valence shell of bromine, uses the correct number. Now each of these atoms has 8 electrons around it. So we can just put the brackets around it, put the charge to the top right. But remember, we always want to minimize the formal charges. So if we actually went through and calculated these, I'll do oxygen first. All 3 of these oxygens at this point are identical. So I'll just do the calculation once, but oxygen has 6 valence electrons as a free atom. And then in this case, each of these oxygens has 6 on their own, and then they're involved in 1 bond. So the formal charge of each of these oxygens are going to be -1. which means to balance it out to a -1 overall, the bromine is going to have to be +2. But if we look at that, we can see bromine as a free atom is going to have 7 valence electrons. In this case, it's got 2 on its own, and then 3 bonds. So when we look at those formal charges, they're not great. Everything has a formal charge, and then +2 isn't ideal for sure. So when we look at this one, we want to think about how can we change it in order to minimize those formal charges. And the thing we're going to want to do is just exceed the octet. Remember, third period and below. Bromine is in is it the third period or the fourth period? Bromine is in the fourth period. Oh yeah, chlorine definitely can exceed the octet. Yeah, so bromine in the fourth period definitely can exceed the octet. It's got that D subshell available. So what we can do is take away 2 of those electrons, or one of the lone pairs, from that oxygen, form a double bond. And now what that's going to do is, if we write the formal charges here, we've got -1, -1, and now we'll have 0 and +1. So we've changed the bromine as well, because now it's got a double bond on that side rather than a single bond. So the oxygen, its formal charge is going to go to 0, which means the bromine is going to go from +2 to +1, excuse me. So what we can then do one more time is just basically that same thing. It's just going to be on a different oxygen. And it doesn't matter which oxygen you pick. If you had the top one, if you had your oxygens in different positions rather than the kind of like the places I have them, you had 2 pointing at the top, 2 of them to the right, whatever. It doesn't really matter with the Lewis structures. But now when we look at these formal charges, whoops, I don't not do that one. Change the color. Now that double bonded oxygen becomes 0. When we look at the bromine now, that'll be 0. We haven't changed anything about that top oxygen, so it's still -1. But now the bromine is going to be 0, because now it's still 7 for the free atom. Oops, still has 2 on its own, but now it's involved in 2 double bonds and a single bond. So now it's involved in 5 bonds. So it's just got a formal charge of 0 in this case. So even though the original structure with just single bonds did check the boxes of a full valence shell, did check the boxes of the correct number of electrons overall, because we can then minimize the formal charges by exceeding the octet on the central bromine. That's why we would have 2 double bonds here, rather than just single bonds all the way around. Let me see how many slides this is. If I just want to do it now or not. Oh, okay. Yeah, we'll just do this now then, just because it's pretty quick. But when we're looking at the covalent bond, the bond enthalpy, bond strength, essentially the same thing, just how much energy does it take to break that bond. And remember, it takes energy to break a bond, which means forming a bond releases energy. So if we took 2 chlorine atoms and then bonded them together, so if we switch this reaction that's shown, then it would be releasing energy. But in this case, because we're separating them, it requires energy. And if we kind of think about why that makes sense, we're going from 2 atoms having a full valence shell to 2 atoms each missing an electron. So it's just going to a non-preferred state. So it's just going to require energy in order to do that. With this, we can look at the table here and see approximate bond energies. But with it, just generally as the bond becomes stronger, what we're going to see is that the electronegativity difference typically is going to increase. And with it, it's tough to look at different atoms. So if you've got like 2 atoms in one bond and then 2 completely different atoms in another, sometimes it's a little difficult. But if you just pick anything that's like fluorine or chlorine, so hydrogen with fluorine or hydrogen with chlorine, fluorine's going to be more electronegative than chlorine. It's going to be a more polar bond. we're going to see that that attraction is going to be stronger. So it's getting closer to an ionic bond, if you think about it that way, as we get more electronegative. So it's just going to become stronger. And then kind of the same thing as they're closer together. So now if we compare carbon and hydrogen with silicon and hydrogen on the left side of the single bond table, we can see carbon with hydrogen has a bond enthalpy of 413 kilojoules per mole. Whereas if we replace that carbon with the silicon, then it drops to 323. So it drops by about 90 kilojoules. And it's going to be because that silicon is going to be bigger. So the bond length, the distance between that silicon and hydrogen is going to be longer. So that bond's just not going to be quite as strong. And that's why when we look at the multiple bonds, those also increase in strength compared to the single bonds. So if we look at carbon-carbon and go from single to double to triple, you'll see it goes from about 350 to about a little over 600 to mid 800s as we go from single to double to triple bond. So because we're just sharing more electrons, that interaction's stronger, so it just takes more energy in order to separate those out. Any other ones to look at? And that's why if you also look at like anything with nitrogen or oxygen, the oxygen bond enthalpy is typically going to be higher than when that same thing's with nitrogen, just because oxygen will be more electronegative. But with that, just looking at the multiple bond table, just also note that's only going to be true for the same type of bond. So if we have carbon with oxygen or carbon with nitrogen, they're both double bonds. That bond enthalpy with the oxygen is going to be higher just because it's going to be more polar. But then if we change that nitrogen to a triple bond and keep the oxygen as a double, the nitrogen stronger. So there's different factors that come into play. So if we want to compare to, if we wanted to predict which is going to be stronger, it's got to be kind of the same type of bond. So it's got to be either all single or all double, all triple. And then one of those atoms has to be the same. Otherwise, it just becomes a lot more difficult in order to actually compare. And then I think I mentioned this when we were talking about single, double, and triple bonds. But I think I mentioned it in terms of the bond length themselves. But depending on kind of what else is around it, because if we're thinking about a larger molecule, it's not just going to be one bond. There's going to be a whole bunch of bonds. And even if we think about like the carbon with whatever here, these single bonds with carbon, carbon, hydrogen, carbon, carbon, it's never just going to be that one bond. There's going to be other things attached to that carbon. And then depending on what you have there, that'll affect the bond strength of the other ones as well slightly. So it's not always going to be exactly 413 for a carbon-hydrogen bond, but it's going to be approximately that. And then depending on what else is around it, it could become a little bit stronger, a little bit weaker. But with this, I think we'll just pause here, and then we'll have more of the practice in the next video.